Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
So we are thrilled to have Gil Fly back. We've missed him over the past few years. By the way, for those of you who haven't seen him talking here before, he loves playing this little thing, right? Not reacting. You want to go stand in front of us? Okay. And he is going to, so he's from Yale and from the University now. And he is going to talk about, is there an interesting, realistic, universal, ridiculous model or noise that reduces, I sat in my own, quantum computation to classical.
Okay, thanks a lot. Actually, yeah, this ridiculous really gives a horizon of new possibilities. I mean, okay, so I'll talk about quantum computation and noise. As you can see, I don't have much background on quantum computation, not to speak about physics. So to this wedding, I come from the side of the noise. Well, I had some. Good. It's good to have Jennifer because she laughs on all the jokes. I mean, even. Okay. Anyway, so this talk represented the work that I did the last months, and so a fuller treatment is in a paper which can be found in my homepage or in the archive. Okay, so let me start by telling you a little bit about quantum computers, and it will be a sort of a story where I'll get some more details at some stage, not all the mathematical details, of course. So quantum computers are devices that are potentially much more powerful than ordinary computers. And the story of quantum computers, like the story of digital computers, in this story, the theoretical model come well before the actual physical device. So in ordinary computers, the model is the model of Turing machine, which in mathematical logic, that eventually later, we know that this have led to actual computers. The analog, the quantum Turing machine, was studied by physicist Deutsch in the mid-80s, and his work had some roots in suggestions made by several physicists, mathematicians, Feynman, Manin, Charles Bennett, and others. And so I think I first heard about this gadget from Giancarlo Rota, who somehow had some paper of Deutsch in the advances. He was very excited. I also was quite excited, although I didn't know anything at that time, not about physics and not particularly interested about complexity theory. Then the subject was picked up by computer scientists like Andy Yao and Vazirani and others. And starting from the mid-90s, it looked that something is going on, and very quickly a lot was going on. So I think the breakthroughs, as I remember it, one breakthrough came with the work of Simon, and he was able to use quantum computers to detect periodicity in a way that it looks completely hopeless for ordinary computers. So more technically, he showed that it's possible to sample for the Fourier distribution of a Boolean function using quantum computers, which seems to be completely impossible for ordinary computers. And as people were contemplating what is the meaning of this discovery and what's going on, a few months later, there was the result of Peter Shor, which shows that quantum computers can be used to polynomially factor numbers to to their prime factors. And this was quite a sensation, a very major event, intellectual event that happened in our lifetime. And after that, there were another important result by Grover, which showed that quantum computer can be used. There is some general speed up for arbitrary search algorithms. Rather than doing the exhaustive search, you can save a factor of square root of the amount of work using quantum computers. So it looks quite remarkable. And the quantum computer defined a complexity class, which is different than things we knew before. Those of us interested in complexity classes, it's a BQP. This is the type of thing that probabilistically can be solved with quantum computers. And it's a very nice class. I think one very promising thing about this class is that it doesn't contain everything. It looks more powerful than classical computation, but only with some special things. And it's a source of a lot of interest since then. Okay, so maybe I should tell you at this part what is the basic difference between classical computers and quantum computers. So in classical computer we have bits, and the single bit can have the value 0 or 1. So this is a single classical bit. I don't know, people who are very familiar to the subject may be bored a little bit. And in quantum computers, we have qubits, sort of the linear algebra, sort of a complex linear algebra analog of the single bit. So the qubit is a vector in a two-dimensional vector space. And the basis of this vector space can be regarded as representing the original classical bits. So we have 0. So this is notation, is the physicist notation. This is one basis element, and this is another basis element. And then the vector can be of the form C1 or C0, 0 plus C1, 1, where C0 and C1 are a complex number, and C0 square, C1 square is equal to 1. And so a qubit is in such a position, so there are continuously many positions, and this position represents a sort of a probability distribution that is familiar from quantum physics, that the bit is with probability. This represents the probabilities of the bit to be in each of these stages. And well, if you don't like this symbolism, you can just write E0 and E1, the basis element, as we like to do this. And these are the qubits. I'll say a little more about what's going on. And so as you see, even by looking at a single qubit, we have here sort of a probabilistic situation. So in general, okay, let me move to close. Yeah, so in general, so this quantum computers fits well with another basic ideas of computer science, that of randomization. So actually, when we have n bits, so let's call them S1 up to Sn. So in the classical situation, when we have n bits, they can be in any of 2 to the n positions, the 0-1 strings. And in the classical, in the quantum computer, the position of the computer can be some complex combination. So if we have the bits, so q1 up to qn, this is the q bit. Then we have s1 up to s2 to the n. This is the 2 to the n possible strings of bits, and the computer can be in a position which is some ci si, sum of ci si, I from 1 to 2 to the n, and again sum of ci absolute value square is equal to 1. And so the quantum computation is starting with some initial position and acting locally, we can modify this probability distribution, and at the end of the computation, so this is one way to look at quantum computation, at the end of the computation we will have a certain distribution described by such a unit complex number of dimension 2 to the n, and then we can measure it, and we'll be able to sample according to this distribution. So in this way to look at it, this extends the notion of randomized computers. We can think about a classical computer, say a computer, and here we can think about some random bits, R1 up to Rn. These are random bits. So a computer with random bits can do a little more perhaps than just a computer, a deterministic computer, and this leads to the class, say, BPP, which is roughly randomized algorithms. And now, instead of using random bits, which are, say, uniformly and independent, if we have a quantum device, we can have our classical computer and feed it. So this is the classical computer, and this is the quantum computer. And this quantum computer can generate complicated distributions, and this distribution we can feed the classical computer. So this model of computation, where we have quantum computer and classical computer, is really excessive. It's a nice way to think about it, but in reality, the quantum computer itself have already the entire power of the classical computer, so we can instead think just about the quantum computer and make all the computation here. But we'll see in a minute that this two way to think about quantum computers will be useful for us. Okay, so this is the story about the theoretical model of quantum computers, and then when at the mid-90s, perhaps even earlier, but certainly when these algorithms, when it became clear that quantum computers can do much better, there were several concerns raised by people, mainly by physicists, and these concerns relate to the matter of noise. So the concern was that that quantum systems are intrinsically noisy. I don't know what precise is the reason for that, but this was the concern, and this may fail all these wonderful algorithms. Now, there were theoretical computer scientists who thought about the effect of noise earlier. There is a work by Bernstein and Vazirani, and they show that if the amount of noise is 1 over n, so the rate of noise, so for every step of the computer, the fraction of 1 over n, where n is the number of qubits, is affected by the noise, then the computation can still go on. But this is also non-realistic, and a more realistic assumption was that the amount of noise is some constant. So for the rate of noise for every step of the computer, the noise, the noise affect quantum information stored anyway, and since also the quantum computer operates some gates, then this also adds some noise. So the amount of noise, the noise affect a constant number of qubits for every step of the computer. So this was the concern, and the question was whether quantum computation can survive with such a noise. And then there was a series of work. So actually this matter was considered already for digital computers, and for digital computers there were some suggestions how to make fault-tolerant computation. I think in reality, the implementation of digital computers, the amount of noise is quite small. So there's no need for a very massive, at least software fault tolerance. But this certainly is a subject of computer science that was studied before. And in any case, so there were several important breakthroughs. So the first concern was the issue of error correction. So, well, I'll talk in more detail about it a little later, but so the first step was to show that error correction, some form of error correction is possible in the set when we have a storage of quantum bits, which can have complicated dependencies, and there are some errors. There are various reasons a priori to doubt if error correction is possible. The simplest error correction scheme in the classical case is to, for example, to replace, we saw it in something similar in Mike Sachs' talk, we can replace the 0 bit by 3 zeros and the 1 bit by 3 ones and apply a majority rule. In such a case, if we have only one error, then we will still recover the original bit. And if we want to imitate this in the quantum case, we see that, first of all, taking some qubit and multiplying it or cloning it is already not possible. And also this operation, well, it's not clear what the precise operation will be. So if we want an operation which will act like this, then it will become non-linear, so it's not a kosher way that we can apply by some a quantum device. And if we extend this operation linearly, then it will not work. So we are in trouble, but it turns out, and this was also a contribution of Peter Shor, that error correction is possible. You can encode you can encode 2 qubits, but you can encode 1 qubit with 5 qubits and still be able to correct any error which affect at most 1 qubit. Yes?
What is an error?
Well, this is a good question, but we'll discuss it later. But okay, it's a good question, what is an error? But naively we can think we have Q1 up to Q5, and we can think about something that happens that corrupt one of them.
But what are these are vectors? Or?
No, let's say that these are the 5 qubits. They live in some complicated. So we have this distribution on 2 to the 5 things,
Okay.
and then something is get wrong for one of them, but still the marginal distribution for 4 of them is still okay. But I think your question is very good, because to say what is the error, we need to perhaps to expand it or to measure it, or we need perhaps to measure the error. Measuring is some operation which affect the things that you measure. So the question what is an error is a good question. We'll come to that. And but actually the lesson from the work of Shor and the work on error correction is that a lot of insight from the classical error correction carries over to the quantum error correction. So somehow you can still represent the error in terms of bases where each qubit can be either, here each bit can either be okay or be flipped. In the case of quantum bits, each qubit can either stay or have 3 types of error attached to it, and there is some sort of discretization of this form.
Qubit again, qubit is what?
Qubit is a vector in situ, a unit vector in situ. So now error correction was the first step. Then come the next step, which is fault-tolerant computation. And here there was eventually the remarkable result, which was achieved in the mid-90s by, I think, 4 groups of researchers. One group is my colleagues, Dorita Aronov and Michael Ben-Or, and the other groups, I don't know by heart the names. One is Preskil, Gottesman, and perhaps another partner, and there is a group by Neil with co-authors, and still another group, and Kitaev, which is a big hero in this field. So there were several groups that achieved the following type of result. The result said that if the rate of noise, so this FTQC is fault-tolerant quantum computation. Fault-tolerant quantum computation is possible if the rate of noise is a small enough constant. I think the The theorems give you a constant of something like 10 to the minus 6, but there are some heuristic which said that this can go up to 10 to the minus 4, something like that. And the noise satisfy a natural property, which is the noise is independent. The noise on qubits is independent. This already requires some work. See, one thing that I do about the noise, I don't regard the noise as a stochastic process in time, but I take a snapshot. Well, I still didn't tell you what the noise is, but I take a snapshot at some specific time. And therefore, then the non-Markovian as function of time is something which I don't consider. But when you take the noise at you take a snapshot at a specific time, you can still ask if the noise operating on different qubits will be independent or a tensor product. And the assumption that the noise is independent, with the exception that, of course, when two qubits are involved in an operation, in a gate, we don't make this assumption. So, okay, but this is something which I'll have to explain. But there is a strong independent assumption, and then if this is the case, then fault-tolerant quantum computation is possible, which means that the model of noisy quantum computers is equivalent to the full model of quantum computers. Now, let me say something. So there are actually two models we can think about, which I already indicate here. We know already that classic computers are noiseless, essentially in the domain which interests us. So this is classical computer. So we can consider noiseless classical computer plus a noisy quantum computer, and we can consider this is called the mixed model, and we can consider only also quantum computer without any, so just a noisy quantum computer. So you see, in principle, you would see classical computers are also, abstractly speaking, they're also quantum computers. They're also built. They also live in our world. So this model, this model is in a sense more elegant. Of course, it's harder to prove theorems for this model, and from practical purposes, you can be satisfied with this model. And what happened was that all the teams, I think only Aharonov and Ben-Or proved the result for this model, and the other teams proved it for that model. And so when we talk about noise, so we will talk about other models of noise, but some sanity tests that it would be useful to do is we will say that a model of noise is consistent if the computational power of these two alternatives is the same. If let's call this the mixed model. This is the pure. If the power of the mix is equal to the power of the pure model, and it seems like a useful requirement or useful question to see if a model of noise is consistent or not. So the result of Aharonov and Ben-Or in particular shows that this noise model, the model of local noise or tensor product noise or probability, or the model where we have independence, is a consistent model. It gives the same power, same computational power is here as it is here. Okay, so this is more or less the beginning. I'll elaborate on some of the things, but the task, so the project that I'm interested is to find models of noise for which a noisy quantum computation reduces to polynomial, to classical probabilistic computation. So this is the question. So it's sort of a rather natural complexity-theoretic question, that can be studied, and I would recommend studying it even in a reality where everybody has a quantum computers in his lap, but certainly in a present reality where this is fairly in the air, whether these objects are realistic, then I think it's quite an interesting problem. So, as I said, as Jennifer said in representing the title of the talk, we will be, it's okay. No, we will be interested in interesting models. And this is something which is hard to formalize. Okay, so perhaps a good interpretation of what Jennifer says, we don't want our models to be too interesting. Yes, I mean, we don't want the models to violate the rules of physics, at least not in a brutal way or something like that. Now, once such models are found, you can ask whether these models are realistic in the sense that they may represent some physical realization of quantum computers. So this can be practical questions for building quantum computers. Certainly, you would like to avoid such scenarios, or perhaps in the worst case, maybe these models are universal in the sense that the quantum noise is actually always belong to this type of model. So this will be sort of bad news for quantum computers, but it can be quite exciting otherwise.
So, for example, no noise at all apparently is not in that category.
Right? No noise at all. Yeah, there is a model. No noise at all is definitely a nice model where the power of quantum computers is the full. This is the original model. The whole problem with noise is that the model of no noise at all, physicists claim this is unrealistic. It's certainly interesting. It's for us mathematicians or computer science, it's quite exciting. If you don't really insist on factoring numbers.
Even for this model, we don't know that it's different from the classical.
Right. No, I didn't even start talking about the problems we have in computation. Yeah, we don't, to really distinguish the power of quantum computation theoretically from P, this is much beyond everything we can hope. It's much harder than NP not equal to P. Okay, but what? And in fact, no, it's just, but in fact, some people really believe, I know, some people when they saw Shor algorithm, the reaction was, maybe this suggests that that factoring is in P. So I think two good reactions to Shor algorithm is, one, maybe factoring is P. Two, maybe quantum computers are impossible. This is the two logical reaction. Or three, maybe it's possible. Let's build them. Yeah.
Just expanding on the earlier question. So the Arnaud-Benor model of noise also the same thing also. It's a model under which noise computation cannot reduce to classical unless
it cannot reduce. Yeah, sure. It has the full power.
More sort of stronger model of noise.
I want more. I want a model of noise. Well, I don't know if I want a model of noise where the noise can be wilder, where there can be dependence. Let's see, independence. If we assume independence, then we are in good shape. Let's drop the assumption of independence. I should say, if you look, the result, the threshold theorems are very promising. First of all, it's really theorems. We don't have theorems which says that when we fly an airplane, not break down. So it's quite remarkable that they were able to prove something. So you would expect that these theorems apply to much more general situation, even beyond the assumption of the theorem. they are very promising. But on the other, we know quite a few cases where the assumption of dependence give you results which are both quantitatively and qualitatively are very far from what you like, I don't know, the stock market or something like that. Okay, so indeed,
People think it's serious.
what? No, it was serious. No, I don't know. No, it was serious. But we'll talk about it later. Okay, I should say that perhaps there were several criticism and some concerns about quantum computation in general and fault tolerance in particular. So when it comes to criticism, there are few prominent people who has angry claims against quantum computers. So for example, Leonid Levin has a 2-page, very impressive section in a paper where he really tears this subject apart. I cannot it's mainly based on practical and physical reasoning. It's very dense. What?
And he's not a physicist.
Okay, but
I
you know.
didn't understand. I mean, from a physical point of view, I didn't understand what he was saying.
Yeah, he has several things. One of his claims, which is that the rules of quantum physics will break down when you need to apply them in such a precision. Of course, you know, if they will break down, it's even better. You know, all you wanted is to factor number, and instead you got a new physics, so you can be much happier. But this is one of his arguments. He has several other arguments. I think it's.
I mean, there are things that they can do with light and stuff on their scale when the uncertainty principle doesn't come into it. So I think
Well,
he's a smart guy, but I don't think he knows.
Oh, okay. This is quite. I can only identify with smart guys that don't know physics. So at least on this is the second part. But the truth is, it's not clear that his paper can be a ground for doing some further research. You can see it as the end of the story, but it's not clear that you can start. And there are some other. There is a famous physicist, which I forgot his name, that claimed that essentially there's no quantum physics. Everything eventually will be based on classical physics. So in particular, well, no, there was Einstein was not, no, there is a Dutch physicist, De Hooft or something like that. And yeah, and there are other claims. But okay, so now this is a critique of quantum computers. There's also what can be regarded as concerns, and in particular, I'm fond of a paper by Alinsky, Horodecki, and Horodecki, which, so Horodecki, and Horodecki is a father and two sons, and they are quantum physicists, and there is another son who is also a quantum physicist, but is not part of this paper, and they analyzed some models of noise, some continuous model of noise, where there is a non-Markovian behavior that they could expect, and they had some concerns that the assumption of the threshold theorem will not be satisfied, and perhaps even in a damaging way. So it's not. You have to show some different phenomena occurring in order to offer an alternative to the behavior. Behavior that is expected by the theorem, and it's not clear why just saying that if the assumptions are not satisfied, then still we will be in trouble. Okay. So now this is the introduction, and what I will do in the talk, so I will present you, I think I'll try to present in some detail one such model. So this will be model number 1, and I will indicate of another potential model, and then this model, to make it work, you have to settle several mathematical conjectures, but in any case, this raises a lot of nice mathematical questions, so I'm quite happy about that. Okay, so let me now describe to you, so I will now repeat our story, but with more details, so I want to tell you what is the model of quantum computers? And I will, rather than talk about Turing machine, I will talk about circuits. So instead of talking about digital computers, a Turing machine is modeling digital computers, I'll talk about Boolean circuits, and then the quantum analog, which was introduced by Yao, is that of quantum circuits. It's more or less the same, up to complexity-theoretic subtleties, which are far beyond me. It's okay. But if not, there are enough people who will stop me. I'm more worried about the physics than the complexity theory. But okay, so a Boolean circuit is something which looks like that. You have some bits. So it's a acyclic, directed acyclic graph. Acyclic graph. You have n inputs, and you have one sink, one output. And the circuit, you can have gates, and these gates, well, let's make binary gates. So this gate, well, let's go into circles. So these gates compute some operations. So the operation, we can take this bit again, compute some operation here, like that. And then at the end, we have the output. And so essentially, this is the model of Boolean circuits. I hope I didn't forget something important. Here we have the original bit, x1 up to xn. We can take the negation of the original bit and put them also here. And then not x1, not x2, not x3, and so on up to not xn. And we can assume that all the gates are either OR gates or AND gates. OR gate and these are AND gates. And this is the output. And you see that this gadget compute describes a Boolean function. So f is a Boolean function. The question we would like we would like to use as the size of the circuit. The size of the circuit. This is the basic parameter is the number of nodes, or the number of nodes altogether. So external and internal nodes. And we want to compute Boolean functions with small size circuits. Yes, Guido. Let me transfer your question to the expert. I don't think so, but if you don't allow negation, does it make the blow-up quadratic? I don't think so. What?
Don't allow negation.
I have you can push all the negation to the input. I don't think so. I don't think it will cause the complexity. Not at all. But if it costs, put them back in their place. I don't, I will not. Yeah, as far as I know, it doesn't cost anything. So this is the Boolean model, and the big question is, of course, so the size is a major parameter. Another important parameter is the depth. So it's how many levels you need to perform the computation. So we would like to prove that problems in A, which are NP-hard, require a super polynomial size or even exponential size. I think we are quite close in the sense that we have a lower bound, or I don't know, 5n or something like that. No? What? Oh, not even. Okay. So for problems which are NP-hard, we don't even have that. Yeah. See, the situation is as far as actually proving things, is quite gloomy. But I think the way we see the world in the Boolean case is quite good, and we don't expect a polynomial size circuits for NP-hard problems. Not even. In fact, we expect an exponential size required for NP-hard problems. So this is the Boolean, the model of Boolean. Another reason why we use circuits rather than Turing machine is that there is a negative result about a noisy computation, which says also of Dorita Aronov and Michael Ben-Or, which said that if we are talking about sequential computation, then there's no hope to do it with noisy, there's no hope to do it with noisy computers. So we need to have quite a substantial amount of parallelism to perform noisy computation. Now, the model for quantum computation is very similar, except here you have qubits. So these gadgets these are qubits, Q1, Q2, up to Qn. And now you allow gates which are some operators, let's say unitary operators, which act on single qubits or double or pairs of qubits, a bounded number of qubits. And it doesn't, like in this case that we could be satisfied with AND and OR, also in the quantum world we can be satisfied in a small list of gates. So for example, we can, the following set of gates are universal in the sense that you can perform anything just with these gates, and this is the gates, one is rotation of one qubit. So we allow, so one qubit is a vector in C2. We allow, so the rotation is a two-parameter family of rotation. We allow any arbitrary rotation. What? One?
Well, one qubit is in C2, sorry.
Two, okay. So it's a two-parameter, two-dimensional rotation plus an important gate which is called C0, which go like this. 1, 1, 1. So it's taking the negation of the second qubit if the first qubit is 1. So 1, 1 go to, so 0, 0 go to 0, 0, 0, 1 go to 0, 1, 1, 0 go to 1, 1, and 1, 1 go to 1, 0. So this is C0, and these two classes of gates are universal. There are other class of universal. So you build a circuit just like this, and then you can compute things. Yeah, I will slow down as much as you want. Oh, what is the rotation? Right.
That's just some kind of a symmetry there, right?
This one?
Right.
No, this is an operation. It's a reflection, yeah.
So you could have said that.
But this is in the space of 2 qubits. The rotation is only on 1 qubit. This is on 4 dimensions. These are the bases. 0 is one basis element and 1 is the other basis element. Well, I should use the quantum, but then it will be just more confusing. It will also confuse me. So these are.
Would it be different if you allow rotations in the pair?
It will not make a difference because we can, to start with, you can allow arbitrary operations on bounded number of qubits, and then there are results which gates are universal. This is example of 2 types of gates which are universal. There are other examples. This is a 2-parameter. You can also have a finite number of gates which are good for all quantum computers. So.
Now, is the real
Okay.
three-dimensional?
What?
Is the real group is 3-dimensional?
No, I think it's 2-dimensional. Rotation of 1 qubit. What? Rotation of 1 qubit. Okay? Okay, so this is the model. Now we come to the noise. So we come to your original question about the noise. The noise is something which is, so one way to think about this is, so you see this quantum computer, we start with C to the 2 to the n, which is the n-folded tensor power of C square, and we have some operator to C to the 2 to the n, and what I want to say. Yeah, and so we can think about the situation where we have initial position, which let's say it's always 0, 0, 0, and then any state of the computer can be regarded as the action of a unitary operator on this initial state. Now, to describe, the noise is a more complicated matter. So let me tell you verbally 2 ways to think about the noise. The problem is that the noise, well, we can think about noise which is only unitary operators on the computers, but this will be a great loss of generality. It's already quite interesting class of noise, but noise usually is a more general gadget, and the way so there are 2 ways to think about it. One way to think about it is to think about the original qubits and the environment of the qubits. And we can think about the environment mathematically as a bunch, for each qubit there is a bunch of additional qubits. So for it, we have the original qubits, they have a bunch of environment qubits, so we have altogether a large amount of qubits, and we take a unitary operator on this large space of qubits. This is one way to think about it. But mathematically, there is a way to think about it just in terms of the original qubits. But this moves us further, so it's more general mathematical objects than unitary operators. I don't think this will be very important for our discussion to discuss them. But when you do this, you have to represent also the situation of the computer after applying noise cannot be represented by just a simple vector like this, but you need a more general mathematical gadget. So one way to think about these gadgets, which I sort of like, you can think about, you can replace each vector 2 to the n vector v by v star or v transpose times v. This will be a 2 to the n by 2 to the n matrix, and then you can think about the convex hull of these matrices. So this is something mathematically that Sasha, you should like, yeah? Like this, you know. Anyway, so the convex hull of positive semi-definite, or the space of, anyway. So, so for our discussion, it's enough to know that the noise is more general mathematical gadget, but we can still think in terms of unitary operators, and this is actually no loss of, this is actually valid if we allow to include also the environment, and if not, we have to do some mathematical gymnastics. Okay. Yeah.
So you allow noise sort of to act only locally on that particular vector in the tensor product and its closest neighbors in whatever order
Oh, okay. So I didn't, the noise, the general noise operator, so you can think about it as, so generally this will, okay, this will be some operator acting, so the unitary noise will be an arbitrary operator on C2 to the n, any, just to start with, then we have to make some restriction. But to start with, it will be arbitrary, and this is even not enough because, for example, measurement is not such an operation, so we need even more complicated mathematical gadget to describe really what kind of noise can happen.
That corresponds to doing the measurement, that once you allow that, then...
Once you allow well, if you allow to consider not C2 to the n, but C2 to the some big M, where M is also the environment bits, then this also accounts for measurements. Yeah. So this is the noise. Now, okay, but now the basic, so the result of Bernstein and Vazirani, which says that if the amount of noise, so although the notion amount of noise still need some definition, but if the amount of noise is small, you can do computation. This applies to any form of noise. But if you want higher amount of noise, then you have to make some restriction. And the basic restriction is that the noise itself is a tensor product. So it acts independently on each of the qubits. This is the assumption, essentially the assumption of all the fault tolerance and error correction results. Now, for the fault tolerance, you need to allow arbitrary action for 2 qubits which are involved in the same gate. And it is known, actually, that you can relax, the theorems will continue to hold if instead of insisting that it is independent on each individual qubit, you only demand that it's independent on, say, blocks of, disjoint blocks of 3 qubits, or 5 qubits, or 7 qubits, then the theorem will still be true, but with a much worse constant. Okay, so this is more or less the state of affair. Now, how this is done? Okay, I should. So here, let me be. I see I'm running out of time, so so I'll give you a schematic way. This is not the most general way, but you look at this operator. So you have this noise. So when you have one qubit, so I will not talk much about error correction, but when you have one qubit, you can every operator on it, even if it's more general type of operator. So you can think about it as a linear combination of 4 types of errors. So one type of error is take the qubit and leave it as it is. So let's call this. These errors are represented by what's called the Pauli operators. So let's call them I, X, Y, and Z. And then any operator, any noise operator, you can represent, like in the case of in classical, you can just look bit by bit and see what happened to each of the bit. Every noise operator you can represent, more or less, it's not precisely true, as a linear combination of things which look like this, say I, X, so C, which is depend on this word, and then you have a word in X, Y, and Z. I, X, Y, I, Z, I, X, I, Y. So this means that on the first qubit, we did nothing. On the second qubit, we apply X. On the third, we apply Y, and so on. So, and then we have a coefficient, a complex. Then we have a coefficient which correspond to this word. And so one scheme of error correction, which is not the most general scheme, but this is a nice scheme. We can take our signal. Let's say we just want to do error correction. So we have n qubits stored, and they had some noise operating on them, and then we can measure the noise. We can measure the noise in terms of this basis. And once we measure the noise in terms of this basis, this determines the noise to start with is some stochastic thing, but then this determines it, so this will give us this coefficient with some probability. This will give us this will determine the noise and give us the syndrome, this is called the syndrome of the noise. And then we look qubit by qubit and reverse this operation. So if we see X, we apply X. So by this way, we correct the noise. So this, if you don't know it in advance, this will not contribute much, but will be very vague. But the important thing is that if the amount of noisy bits is not too large, so if there are not too many, if most of the things here are I, then this will work. Now, what is the what? Yeah, so you have to undo the rotation, unrotate this rotation. Now, what make fault tolerance or error correction possible? If you assume that the rate of noise is epsilon times n, now, and you assume that the noise is a tensor product, then it's quite easy to see. So this means that on each bit, the noise has the form identity plus sign rho I, and then you have identity plus rho 1, tensor identity plus rho 2, and so on. And this will imply that above epsilon n, the number of the contribution of coefficients where the noisy bits will be larger than epsilon of n will drop exponentially. So, if the noise is 1/1000, in all this expression, you hardly see a word where the rate of non-identity element will be more than 1/1000. And if this is the case, and also there is some symmetry argument, if this is the case, then the codes will correct it in the error correction, and the fault tolerance, well, you have to argue that you can maintain the error at a low level. Okay, so this is very roughly the reason why error correction and fault tolerance works, although there are substantial technical difficulty, especially to deal with gates. Okay, now I come to the models, that model of noise that I want to suggest to fail. Yeah. Well, actually, this. Yeah, so for general noise, these coefficients can be they can be even vectors. which will represent the environment. But the important thing, if you do this scheme of error correction, once you do it, then it becomes probabilities, and then you sample this word according to some probability. So then you don't have to worry about it. But in general, when we talk about general form of noise, these coefficients can be also tricky because they can be actually vectors which correspond also to the environment or something like that. Okay. So so
Still, the magnitude squared will be a probability of the whole system.
right. Once you measure it, the sum of the magnitude square will add up to 1. So this will be. Yeah, right.
Is it true that you can measure once, or because after that the whole thing sort of destroys itself, or?
Yeah, when you measure something, then you force it to collapse to the thing. Yeah, but no. Once you measure the noise, you determine the noise. So here we don't measure the signal. The nice thing of this scheme, you measure the noise without touching the original signal.
Oh, you do.
So you measure the noise. This determines the noise. The noise collapsed to a specific position, and you correct it, and you are left with the signal. So this works. This is very remarkable. Yeah. Okay. Anyway, now we come to my suggestions. And let me start, I said there are two. Let me start with suggestion number 0, which is something which is not good, but I think model 0. So this is something which was considered, I mean, not studied, and suppose we take, say, a unitary noise and take a random rotation, so a random small rotation of c 2 to the n. So I want to start with this to say why this is bad, or what happened in this case. So this is something that actually, when you look at the papers, say, this will fail the computation entirely, but it's unrealistic. We don't have to worry about it. Indeed, it seems rather unrealistic that the noise will take all the n qubits of the computer and make a random rotation in this huge space. Okay, now let's look a little bit about this noise. So first of all, it is a rather interesting. So it's both ridiculous and interesting. Ridiculous from the physical, but it's interesting, and also in particular because I don't know precisely what is the computational power of a quantum computer with this amount of noise, which is a little annoying. No, it looks that if the noise is small, at least classical bounded depths. Let's talk about we had the pure and the mixed model. So in the pure model, it's quite certain that bounded depth computation will survive because in this assumption. It's not clear if bounded depth quantum computation will survive. This I'm not sure. Still, it's quite low. Of course, in the mixed model, we have the full power of classical computation. So maybe we can have, on top of classical computation, also bounded depth quantum computation, which may actually give advantage. So this is also a major problem in complexity theory. What is the power of classical computer plus bounded depth quantum computers? It may be slightly more powerful, but I'm not sure that all the bounded depth quantum computer will survive. So this is an interesting complexity theoretic result, which is not answered. But what you can see here, quite for sure, that this model is very inconsistent, or at least apparently, because the pure model will have very small amount of computational power, and the mixed model will have something above, which is at least BPP, maybe higher. In any case, because, okay, so this is the situation for this. Now, what will be, you see here, it was crucial to understand the expansion of the noise in terms of Pauli operators. And you see that the crucial things about it, now this will be, this is the punchline of the example which will come. So the crucial point in the argument of the fault tolerance is that we have exponential decay for coefficients where the non-identity terms are numerous. What happened for a random operator? What can we expect for a random operator? we have a random operator without any locality assumption, so this computation does not work.
So uniformly random.
Let's say uniformly random, we have a uniformly random rotation, and we know that the rate of noise is epsilon. So for example, we know that each non-identity element appears here with probability epsilon. What kind of coefficient we will have? So this is a standard thing in the sort of concentration phenomena point of view. You see, we have so many more coefficients where in a random coefficient, only quarter of the letters will be the identity. So if we take a random rotation, even if we assume that we have this epsilon, we can be quite sure that most of the weight will be on words which involve at least 74.99% of non-identity letters. So it will be very different than the type of behavior we see for the local noise. So just because this is the bulk of the coefficients. Okay, so a random small noise can be very bad for error correction. It will have the way it will behave very different than what we think about noise. The way it will behave is that it's something like there will be a large probability, say epsilon, a little less than epsilon, that 75% of the qubits will be corrupted. This is not what we think intuitively about noise, but this will be the effect of a random noise. So now we want to understand fault tolerance, we have to decide if this is the more close to reality situation, or maybe the concentration of measure will somehow still win, even if we just relax a little bit the locality condition.
Well, if they're small, meaning that they're close to the identity, right?
Yeah.
Almost you can make it commutative, right? Instead of multiplying, just add a symmetric matrix to the.
It's not so small. It still affect epsilon of the qubits. Well, I don't know.
Okay.
Yeah, I don't know. I mean, I don't have a very. Okay, so now let's say this is not so. This model is not realistic. It also kills. If you have, there are various arguments against quantum computation, and some of them are so successful that they also apply against classical computation. Like the recent thermodynamic argument, which seems quite powerful also against classical computation, but probably classical computation. There is a recent paper by Lidar, Aliski, and some other guy. Yeah, so you should look at it. Anyway, so. Okay, so now let's change it a little bit, and the model 1, so it's not so bad, but this time, okay, so I see I will not get at all to the second model, and I'll only talk about that. So now let's assume that we take the noise is a product, so the noise is a product of operators, each acting on a small number of qubits. So the noise is a random product of operators acting on k qubit with probability, say, pk, k equal to 1, 2, and so on. And yeah, this is it. And the random product, unbiased random, it's very important, unbiased random product of operators acting on k qubits. Now, if you have this scenario, so again, now it's only come from only heuristic argument, it looks that, well, it depends on this distribution of pk, but no matter what the distribution is, if this distribution is positive, then, and it's not clear to me what happens if this distribution is truncated at 0, even on the heuristic level. If this distribution is positive, but decaying as fast as you want, then still, as far as the Pauli operators, you will still have a substantial amount of coefficients where the non-identity elements will be substantial, above 74%. So this is the the heuristic claim. Intuitively, the argument might be is that, you see, just on these k qubits, a random operator will create a substantial dependency between the error occurring on these k qubits, and this will accumulate to create a large coefficients of these words with many terms which are non-trivial. Okay, this is, by the way, this is a heuristic argument which is fairly dubious. So this is a very...
But K is fixed.
No, K is not fixed. This is a distribution, and but this... But K...
For all K.
But pk can be 1 divided by 2 to the 2 to the k. Okay, so... Yeah, it should be positive for the k. But, probably in order that this will work... Okay, so now the heuristic conjecture is that this type of noise will create high non-trivial Pauli operators. But nevertheless, if you look at this will still can be correct. So the question is why classical computation will prevail. And if you look at it, this type of noise can still survive by classical computation because majority is quite powerful. Majority can, in classical computation, the most naive thing you can do, and actually this is how computers are built, is to replace every bit by a huge number of other bits and take the majority function. This type of error correction is immune under noise, which unbiased noise, which affect say 1 minus epsilon of all the qubits, of all the bits. Still, this majority will recover it. So if you take the majority, the linear extension of the majority operator in the quantum setting, you can still do, still can do classical computation under this noise, but this will kill the possibility to have excessive power for quantum computation. So this is on a very heuristic and it's level. The idea, to translate this idea to reality, you have to prove all sorts of statements, which may or may not be true, but you are welcome to look at the paper. And there are all sorts of nice statistical physics type models of, say, random quantum programs. This is the issue that arise, which seems to be of independent interest. I'm the only one. I'm the only one who is doing that at that stage. This is the time to get on the train.
This is time to jump right in.
Jump right in.
Right.
Yeah. Okay. Good.
Somehow related to the question, how well can you generate a random operator by sort of superposition of small dimensional rotation? Because it looks like it may be well reducible to model 0, right? How can you tell this?
No, okay, this point. You see, we don't, this is a good point, because one thing in favor of model 0 is that although it seems unrealistic, the insight we have in theoretical computer science is that by local operation, we very quickly converge to a rather random-like a gadget. So I think in this situation you will not convert to a random type gadget, but you will convert to something which has a lot of the properties of a random type gadget.
I think that's how, for example, MATLAB generates a random unitary matrix if you want to.
But you don't want an arbitrary random. You want to keep the rate error to be small. So this is still it's slightly different restriction. Okay. Thank you.
Tomorrow and soft.
So that is